Section 9.3 is about the general theory of convergence and divergence of series, though I will approach this considering examples. And the first example we're going to consider is one where the convergence or divergence is relatively easy to figure out. The series itself is a little strange looking. I'm going to use K as the index of summation. The book often uses N, but I have a pedagogical reason for using K. And again, I make my lowercase k's cursive. That is a K. Summation K goes from 1 to infinity of 1 over K squared plus K. Kind of a strange looking thing. I'm picking this example because it's doable. Okay, it's a nice example to illustrate ideas. You want to get used to writing summations and understanding what they mean by also writing them out with plus dots. Do it both ways. Maybe on every single problem you do, get practice thinking about it both ways. It's easier to think about it writing it out, but that emphasizes what this means. First, start with K equals 1. Then go up by 1 to K equals 2. And the summation means you just keep adding these things. There's the pattern. Then if you like, you can simplify that. That becomes 1/2 plus 1/6 plus 1/12 plus 1/20. The next one would be 1 over 5 squared plus 5, which would be 1/30. This is the series that we're considering right now. We say it's an infinite sum. Technically speaking, that's a convenient fiction. Nobody can literally add infinitely many things. Nobody. We're pretending to. Partially because it's fun, partially because it is useful. It is actually useful to pretend you're adding infinitely many things. What's really going on is an underlying limiting process. There's a limit. If the limit exists, we say this series converges. If the limit does not exist, we say the series diverges. But what do I mean? What limit? We have to consider the corresponding sequence of partial sums. The things that we are adding here are called the terms of the series, typically denoted by the letter A. And the kth term here, A sub k. The A's themselves form a sequence, but I'm adding the A's to get a series. Sequences in section 9.1 is important for series. You can't understand series if you don't understand sequences. The A's themselves form a sequence, but we also have a sequence labeled S sub n that is called the sequence of partial sums. This is the kth term. Sn is called the nth partial sum. It's the sum of the first n terms. Sum k goes from 1 to n of ak. It's a1 plus a2 plus a3 plus ... plus when k is n, it's the last term is an. That's a finite sum. No problem giving meaning to it. Now, n could be humongous, could be a million, could be a billion, could be a Google, right? 10 to the 100 power, more than the number of atoms in the universe. Way more, by the way. Trillions of times more than the number of atoms in the universe is 10 to the 100 power. I'm not saying you could do this sum in a small amount of time, but I am saying the sum makes sense. Theoretically, if you had enough time, you could do it. Though if n were a Google, this would be so unimaginably long. It just, you don't want to really imagine it. I mean, you could do it in heaven, But would you really want to? Probably I would not even want to. Okay. I would now want to just keep going with that. I have other things I'd like to do. All right. That's the nth partial sum. The key question is, does the limit of that n partial sum exist? If it does exist, if this sequence of partial sums does have a limit, we say it converges, and we also say the series converges. The infinite sum, quote unquote, sum, to that same limit. And we even write it that it equals the limit, even though we're not literally adding up infinitely many things. We're pretending we are adding up infinitely many things. If the limit does not exist, then the sequence diverges, and we say the series diverges. So, does this limit exist or not? In this example, it can be fairly easily figured out, but it does involve a trick. A trick that's an old friend from a month and a half ago. Partial fractions. Oh, really? You thought you'd never see partial fractions again. No, we are doing it again. It has other applications as well. If you take differential equations, Laplace, partial fractions is useful for something called Laplace transforms, which is useful for solving certain differential equations. There's other applications as well. I'd like to find A and B where this is true for all values of K. We could pretend K is a continuous variable if you like when we think about this expression. You don't have to. Multiply both sides by the common denominator. By the way, I should emphasize that K squared plus K can be factored as K times K plus 1. I should have emphasized that. Well, the whole thing here is 1 over that. So multiply both sides by that common denominator of K times K plus 1, getting A times K plus 1 plus B times K equaling 1, right? Looking at these two things here. Multiply both sides of that equation by K times K plus 1. K's cancel in this term, giving you a K plus 1. K's plus 1's cancel in this one, giving you a K. And you get complete cancellation of the K and K plus 1 here, giving you a 1. Pick your special values to solve for A and B quickly, like K equals 0 implies you get A equals 1. And K equals -1, even though in the series K was not -1, in fact, it was also not 0. It does help us solve for A and B. We get that B is -1. So what does this mean? So Sn for our example, sum K goes from 1 to n of 1 over K squared plus K can be written, sum K goes from 1 to n of what? Of this thing here in parentheses with A equal to 1 and B equal to -1, like this. Now, when you look at that, it doesn't seem like we've gained much, but we've gained a ton, because if you write this out without a summation sign, when K equals 1, it's 1 over 1 minus 1/2, 1 minus 1/2. When K equals 2, it's 1/2 minus 1/3, right? When K is 2, you get 1/2 minus 1/3. When K equals 3, it's 1/3 minus 1/4. When K is 4, it's 1/4 minus 1/5. Keep going, ... Let's write the last three terms. When K is n minus 2, it's this. When K is n minus 1, it's this. And when K is n, it's this. And amazingly, something really cool happens here. This is a finite sum. I got these parentheses. The associative law allows me to get rid of the parentheses and just cancel a bunch of stuff here. Dot, 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 dot. Something there cancels with that. Something there, those cancel, these two cancel. And I'm left with a simplified formula for Sn of 1 over 1 minus 1 over n plus 1, which can also be written as, when you subtract these fractions, cancel the ones up top, n over n plus 1. And this is now something that pretty clearly, I hope, in looking at these formulas, has a limit as n goes to infinity of 1. If you think about it that way, it's like a rational function of n, where the numerator and denominator have the same degree. The plus 1 doesn't matter much in the long run. You've got effectively n over n, 1. Gets closer and closer to 1 as n goes to infinity. Here, that also gets closer and closer to 1 because you're subtracting something getting closer and closer to 0. This goes to 1 as n goes to infinity. It never equals 1 because n never reaches infinity, right? In the standard real number system, infinity is not a number, so we don't literally plug in infinity. It never equals 1, but it approaches it. It gets arbitrarily close. We can make it as close as we like to 1 by letting n be sufficiently large. So we say the limit exists, n equals 1. Therefore, our original series could be said to converge to 1. It converges to 1. And we write that the infinite series, the infinite sum, actually equals 1, as if we had literally added up infinitely many things. But remember, we aren't literally adding up infinitely many things. We are just pretending to. But this pretending has been made rigorous by the idea of a limit. Everything in calculus is based on limits. That's what separates calculus from algebra and pre-calculus, is the limits. Derivatives are based on limits of difference quotients. Integrals are based on limits of Riemann sums. Improper integrals are limits of proper integrals. Series, infinite sums, are limits of partial sums, finite sums, as the number of terms goes to infinity. We write equals 1, even though we didn't literally add up infinitely many things. And even though the SNs never equaled 1, they approached 1. Okay. So this example is kind of nice. Effectively because Sn has a simple formula. But that's very, very, very unusual. It happens with geometric series. It happens with examples like this where you can use partial fractions and a bunch of stuff cancels. That's called telescoping, when a bunch of stuff cancels. I think that's a weird word to use, telescoping. Telescoping sum. It'd be better to call it a collapsing sum, I think.